came up with this idea of atoms, that an atom is the smallest piece of something, an indivisible sort of chunk of something. He gave them their name, atomos, from that Greek word, meaning indivisible. Then people sort of forgot about atoms. Didn't really explore atoms any further until some new technology started to be developed. And in the 1800s, scientists really started to look at chemistry and started to understand what matter is made out of. It was Dalton that came up with the ideas about elements being different types of matter that could combine to form compounds. Okay? But his thinking was that atoms are these solid chunks of stuff. J.J. Thomson, later on, the end of the 19th century, came up with the plum pudding model. He discovered electrons existed. He knew they were negatively charged. And so his idea was that the atom is a chunk of positive matter with negative electrons sort of sprinkled throughout it. But he still, again, thought it was a solid chunk. Rutherford, who we know now, came up with the idea that most of the atom is actually empty space. So his ideas led to us understanding that the nucleus is a very, very small, positively charged part of the atom, and then the negatively charged electrons are out of the nucleus, scattered in a very wide area with mostly empty space. That's the Rutherford model. Bohr, later on in the 20th century, came up with the planetary model. We started to identify that there are these different electron orbits, energy levels, that the electrons can exist in. Okay? And he described them that way. We know today they're not actually in these sort of circular orbits flying around the atom. We know that there are different energy levels, and now it's called the electron cloud, and that there's different probabilities that electrons are in different areas, so it's a little more complex than what Bohr said, but the idea is useful. So that's the sort of overall history of atomic models. There's some neat things we could show you. We don't have time, but it's interesting to learn about the history of the periodic table of Mendeleev and how he put it together. I'll show you this video, though. It's just pretty quick. It's about Rutherford's experiment, sort of recreated using modern tools. Okay? So we can see what it sort of looked like.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be nuclear helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. hits it head on and just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing them at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small, and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Alright, so you see there just basically the same idea that Rutherford did, but using some modern equipment. Alright, so we need to talk today about molecular weight and how we can find the mass of a molecule. So, if we look up here, we have some definitions. Compound, first of all, we know is two or more elements joined together. What compound are we looking at here?
Water.
Water. How many water molecules is this formula referring to? 4. 4 water molecules. That's what this 4 that comes before the H2O stands for. We call that a coefficient. It's a large number, it's directly before the compound. That tells us how many molecules of the compound we have. That's different than what we call the subscript. What's the subscript in this formula?
2.
It's that 2, that small 2. Okay, it's usually written smaller and below one of the elements. What does that 2 go with? Goes with the hydrogen. Refers to the hydrogen. Tell us how many hydrogen atoms there are. And we use these subscripts and coefficients to help make our formula neater, easier to understand, and so on. I mean, we could write these formulas without those. Like if I write it without a coefficient, I could write H2O, 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 H2O. But it's just kind of tedious. I could also write it without the subscript. I could just write 4HHO. There's 2 hydrogens, 1 oxygen. But that's not the way we generally do it when we're referring to these compounds in chemistry. We use subscripts and we use coefficients. So our first step in what we want to do is figure out how many atoms of each element there are in a compound. So to do this, so if I have aluminum oxide, Al2O3, my first step is I'm going to list the elements that are present in this compound. In this case, it's pretty simple. There's just 2 things, aluminum and oxygen. My second step, I write down how many molecules of this are there. How many molecules of aluminum oxide are being shown here? Matt?
2.
No? Peter?
1.
Just 1. There's no coefficient, which means 1. Okay, how many atoms of aluminum are there in this? Matt?
2.
2. giving us 2 total atoms of aluminum. How many atoms of oxygen are there? First, there's 1 molecule total. How many oxygen atoms, CC? 3. Multiply them out. You know there are 3 oxygen atoms. Now, this is a very simple example. We're going to get more complex. So that tells us how many atoms of each element there are in this compound. Okay. Well, sometimes we also use parentheses in a chemical formula. So here we have NO3 parentheses 3, nitrate then. So this first subscript, this 3, what does that go with? What does that belong to? The oxygen only. How about the 3 after the parentheses? What does that apply to, Jimmy? The whole thing. Whole NO3 molecule. It's the nitrogen and the oxygen. Peter?
Is that another way to do
The coefficient?
yeah.
Sometimes, but often the parentheses are used just to modify parts of the molecule, like we have here. So now we have something a little more complex. We have 3H2CO3, 3. Again, let's follow these steps. First, we list the elements. There's only 3 elements here in this compound. Hydrogen, carbon, and oxygen. All right, let's start with hydrogen. How many molecules of this whole compound are there? 3. We look at the coefficient. There's 3. How many atoms of hydrogen? 2. How many total atoms of hydrogen then? 6 total. So multiply with that. Okay, let's look at carbon. First, how many molecules of this compound are there?
3.
No, 3. Now we're looking at the coefficient. How many atoms of carbon are there inside?
1.
Well, there's 1 here, but is there another subscript that goes with it?
3.
That 3 as well. It's 3 total carbon. For a total number of atoms of carbon?
9.
Of 9. Oxygen. How many molecules of this compound are there, Peter?
3.
3. What's oxygen? How many oxygen atoms are there in this? 3 here and 3 there, so 3 times 3? 9. So the total number of oxygen atoms?
27.
27. So now we know how many atoms of each of those elements are present. Okay. I'm going to add one more piece to this, that you will also want to know what is the atomic mass of this whole thing. How would I do that? Not quite, right?
You get the AMU of one of them multiplied by the number of all the way on the right.
Yeah,
Then and once you get all of that, you add all of them.
exactly. I find the atomic mass of hydrogen, it's 1, and there's 6 atoms of it total, so I can multiply it out. Carbon, there's 9 atoms, so 9 times 12, and 27 times 16, and add those up. That would tell me the mass of one of these, of this whole compound. And that's what we're going to do here. So let's start with some simple examples. Sodium nitrate, NaNO3. First, what are the elements present in this compound? Which elements are present? Somebody raise your hand. Ryan. Sodium.
Okay, sodium, nitrogen, and oxygen.
Sodium, nitrogen, oxygen. How many molecules of this thing are there? Linda? 1. Coefficient is 1. Okay, now let's go through sodium. How many atoms of sodium are there? 1. How many atoms of nitrogen? Is it 1 or is it 3?
1.
1.
3.
Because the 3 is where?
Parentheses.
Inside the parentheses next to the oxygen. And 3 oxygen. Now we need to know the atomic mass. What's the atomic mass of sodium?
23.
23. Nitrogen
14.
and oxygen
16.
60. Okay? Last up, multiply the number of atoms times the atomic mass, 23, 14, and 48. 3 times 16 is 48. And finally, add the atomic masses together for a grand total
85.
of 85 what? Veggie burgers?
No,
AMUs. 85 AMUs. So that means the mass of one of these sodium nitrate molecules is 85 AMUs. This next one's super simple. This is hydrochloric acid, HCl. It's got hydrogen, it's got chlorine. One molecule, one atom of each. Have you memorized it yet? What's the atomic mass of hydrogen? 1. Chlorine?
35.
35 AMU. Total mass of hydrochloric acid molecule?
36 AM.
36 AMU. All right, too easy. Another one that's too easy. I don't even know why it's on there. Carbon dioxide. It's carbon, there's oxygen. How many molecules? 1. How many atoms of carbon?
1.
How many carbon atoms of oxygen?
2.
Atomic mass of carbon, you memorize it yet?
12.
Oxygen,
16.
that one you'll know by heart. Multiply them out. 12,
32.
32.
44. And
Total mass,
44.
44.
AM.
AMU. What's that? Yeah, no, we did that. All right, think you're tough now?
Sure.
All right, what's the next one? All right, see if you really are tough. What? You did this one already? You done? All right, so we pretty much gone with that one? All right. Elements. Carbon, hydrogen, oxygen. How many molecules? 4. Atoms of carbon is 12. I did the multiplication already. Because there's the molecules is 4 times the number of atoms, which is 12. 88 total atoms of hydrogen. How many oxygen? 44.
Wait, is that supposed to be in matchbox? No.
Nope, that's not the atomic masses. What's the atomic mass?
No, this is the multiplier.
What's the atomic mass of carbon?
So you don't know. Oh, wait, never mind.
Atomic mass of hydrogen
1.
and oxygen?
16.
You guys forgot to do some multiplication, didn't you?
I did put it in the box.
All right, so what's the total mass of the carbon?
576.
48 atoms of it. Each atom's 12. What is it?
Oh, so I did this.
How about the hydrogen?
88.
Oxygen?
So 704.
Total mass?
1,868.
Yes. 1,368 atomic mass units. Alright, do the bottom one if you really want to challenge.
Yes. Oh, yeah.
Come on. I'll show you this one.
Wait, is that chlorine or odd?
It's chlorine.
You had me think that one. So, it's gonna be intense.
Do we have any chemistry all-stars? We're going to finish the last one before the bell rings?
Go. I have a huge star.
What?
Nick.
You disgrace us.
Because you got that warm-up on your desk.
It's some number in the university number.
That's your homework.
Homework. What's your do all
Yes.
You know if your dad came with all of its sauce?
No.
You should learn.
There you go.
Oh, CL. 7,600
Rosemary, what happened here? You at a standstill, a roadblock? Anybody, last one? You got 30 seconds. Jimmy, no, nothing? Who? GC? Almost. Almost?
I got the second to last one.
Is it right?
Yeah!
Brian? Come on, you're my only hope, Obi-Wan.
I got it.
What?
525 in there. 5. Wait, yeah, 5 in there. Right?
Wait.
What?
Wow.
No!
Who-
How'd you get 59?
Where?
How'd you get 59?
There's some chlorine. 3 times 1 times 3 is 9. How do I get 9? Because look, there's 3 now. 59?
Yeah.
That's the atomic. You got it?
I got it.
That's, you got it on your own?
720.
Oh, you got it, CC.
24. I got it to look at the screen.
All right, that's your homework I gave you. There's 8 problems, some of which are quite complex.
I'm not going to be able to do it.
I don't think we got a lot of them. That's what you really do. You go office and immediately back to class. See you later.
I need to hear Natalie! How does it feel, Chloe? She's so mean. She let me last time.
What?
She let me last
Chloe?
time. Yeah.
See? What's good for the goose is good for the gander.
What?
You ever heard that?
No. What?
What's good for the goose is good for the gander.
What?
So, Google.
Are you comparing someone to a goose?